Welcome to Lecture 6.3b. In this video, I'm going to show you how you can apply the integration by parts formula to solve a number of different problem types. To start, it continues to be really important that you're able to recognize the difference between when you should use integration by parts and when you should use substitution. I think that you're probably clear from class, but let's just do a quick check. Look at A, B, and C and pick a strategy for each one. Nice. So you saw the answers in Edpuzzle, but here's just a quick reminder of the thinking process in case you got one wrong. In both A and C, I saw a function and its derivative next to each other, and that's how I knew to use substitution. If you thought that B was also substitution, you may have made the mistake of kind of disregarding this exponent 4. You are right that ln has a derivative which is 1 over x, and it kind of looks like that's what's going on here. But actually, the x to the 4th is a totally different function from 1 over x, which is why substitution won't work. If you still doubt me, try setting it up. You're going to see that after you make your substitution, you still have x's left, which means you can't use that strategy. How about D, E, and F? Nice work. So these were slightly trickier. For D, there is actually something in its derivative here. It's just a little bit tricky to figure out what the something is. Think about the inside function here. Remember that substitution is just the integral version of the chain rule. So if the inside function we choose for u, then its derivative is just 2 dx, and we don't see a 2 out front. But you can just divide by 2 to kind of fix the coefficient. So I actually would use substitution for this one. E was a pretty classic integral by parts situation, 2 separate functions, one that we can make disappear, and then cosine, inverse cosine is obviously one where you always use integration by parts. Great. Let's move on to something more interesting. Take a look at example 1 right here. This is going to be an integration by parts strategy. What would you choose for your u? Right, so the right choice for u here would be x squared. So when you set up integration by parts, we start by picking u and dv, and together they should make up the whole integral. And then you find v and du in order to apply the formula. Once you get good at this, you can probably do this without writing out all 4. I'm going to do it like that. If you're still struggling with integration by parts, you should write out u du, v du. Okay, I start with u and multiply it by v, and then subtract v du, the integral. You can double check. This is du, the derivative of x squared. This is the antiderivative of sine. Just to clean this up a little bit, I'm going to simplify and get rid of some extra negatives. I just canceled out those and moved the 2x in front. Now normally if integration by parts works, I should end up with a new integral that's somehow easier to solve. But this actually isn't an integral I can do in my head yet. And you might think, oh, well, we did it wrong. We actually didn't do this wrong. We just need to do this again. Given this new expression, which has to equal what I started with, and is a little bit simpler because the x squared is now just an x, I want to take it another step. So I'm going to keep the first term, and I'm going to pick a new u in dv for this new integral. Again, I chose cosine to be my dv. In general, this first term, x squared, which turned into 2x, should continue to be your u. If you imagine, on the next step, we're actually going to wipe out the x, and that's when the integral will be easy to solve. Using my new u in dv, I'm going to apply the integration by parts formula a second time. Since u is 2x, du is just going to be 2 dx. And since v is cosine of x, since dv is cosine of x, v is going to be sine of x. And now we have an integral that we can solve. This middle term is just another term in our answer, so I'm going to bring everything down. And the integral of 2 times sine of x is just negative 2 cosine of x. Along with that negative right there means I'm going to have plus 2 cosine of x. And don't forget, plus c. And that's your final answer. So if we zoom out here, big picture, we used integration by parts the first time, but using it once wasn't enough to completely simplify the integral. So I applied it a second time and was able to get an integral that I could solve just in my head, which is how I got my final answer. Don't forget to continue to bring down that UV term each time you apply the formula. Use this same strategy to solve the one for u. Nice work. So this one took 3 integration by parts, which you can kind of guess because you'll take 3 derivatives in order to get x cubed to kind of completely disappear. I'm going to scroll through my work. Here's the first integration by parts, and then the second integration by parts, and the third integration by parts finally gives us a very simple integral, and there's your final answer. If you need to see that some more, feel free to pause and go back and look at it. Cool, so we'll move on. This is now another way to use integration by parts creatively. This strategy that I'm going to show you right now, which is solving for an unknown integral, is a pretty rare thing, but it is very elegant, and it's something that you'll definitely need to know and could come up in some situations. So just like before, we'll start by using integration by parts as if we were just getting a normal integral. In this first example, there isn't an obvious choice for u or dv, so it actually doesn't matter. We'll just choose e to the x for u and cosine for dv. If you have not, in previous examples, kept all of your work in one line, this is where you need to start doing that, because what we're going to do is actually a little bit different. We're going to bring this left side of the equation down as we do each step, because we're going to end up using it like an equation. So go ahead and don't write your next step on the next line. Write your next step off to the side, which is exactly what I'll do. You know the integration by parts formula as well as I do by now. Start with u times v and subtract the integral of v du. Now, just like the previous example in this video, doing integration by parts one time leaves us with an integral that's still kind of complicated. So we're going to do integration by parts again, and the only thing different is I'm actually going to rewrite the original expression on the next line so that I'm keeping both the right and the left side. It'll look like this, and then in the brackets right here, I'm going to take this integral using a second integration by parts. So that means we need to choose a new u in dv. Now, notice the similarities between this integral and the one we started with. They both have e to the x and they both have a trig function. It's very important that you continue to use consistent u's and dv's, even though it didn't matter which one was which at the start. Since I chose e to the x to be my u the first time, it's important to choose e to the x to be your u again the second time. And that means the trig function is going to be my dv. So the dv is a little bit split from the dx, and that's okay. The order doesn't matter. If you chose backwards and you chose u to be sine, you would actually basically be undoing what we just did, and you'd end up with the same integral over again. We want to continue the process, so I'm going to choose e to the x to be u again, so I'm consistent. Once I've got u and dv for this new integration by parts, I'm now going to complete the actual formula. U times v is e to the x negative cosine of x. I'm using new u's and v's. Don't get confused with your old ones. And then we subtract the integral of v du. And I ran out of space. Sorry about the messiness. Okay, I want to clean this up a little bit. You may see a problem. Hold on for a second. We'll see if we can resolve it. When I cancel these negatives and distribute this one, I end up with an expression that looks like this. Now remember, the right side is what we've been working on, and the left side is just the original problem I keep bringing down. So I alluded to a problem a second ago. Well, the problem you might have seen is that we still have this integral symbol, and it's an integral that we don't seem to be able to evaluate. We can't seem to find the antiderivative. And that's true. And so this is where this really elegant, brilliant trick is going to come into play. What do you notice about this specific integral? It just came from this one right here. I switched the order, but that's okay. What's so special about it? So I don't know if you saw it or not, but this is actually the exact same integral as the integral we started with. And now, if you kind of like take a big step back and look at the structure of what we got, I'm going to think of this just like in algebra where you have some x, and that x is actually on both sides of your equation, but you're trying to solve for what x equals. Well, if I have this x over here and another x over here, in order to figure out what x equals, I would move them all to one side of the equation. So I can do that here with this big crazy expression I'm trying to solve for. I just need to add that same integral on both sides of my equal sign. And I am allowed to do this because that's just the rule of algebra, right? You can always do the same thing to both sides. I want to do this because now this is going to cancel out that integral. And this integral plus itself, I can write really simply as just 2 times that same integral. So if I bring the rest of the right-hand side down, I'm now really close to knowing what this integral equals. All I have to do is divide both sides by 2, and we actually see that this integral that we started out, that we were trying to figure out, has to equal this expression, and this expression is a function. It's not an integral anymore. That's the answer. I'm going to zoom out so you can see the big picture here. All the colorful part at the top was integration by parts, and then at some point we just turned this into like a basic algebra problem where we were solving for this integral. See if you can replicate this process and do the one at the bottom. So this is very similar. I'll scroll through my work here. This is for the example that you did. These are the first 2 integration by parts, there and there. And then we treat it like an equation, adding this original integral over to get 2 of them, and ending up with an equation. Kind of miraculous. Okay, it's downhill from there. The last 2 things I'm going to show you are actually things that you already know, and I'm just going to prove to you that it's connected to integration by parts. Remember differential equations? These are equations where you're given information about the derivative, and I can ask you to find either a general or a particular solution. Remind me, what's the difference between a particular solution and a general solution? Exactly. A general solution has plus c and represents a family of functions, whereas a particular solution represents a specific function, which means you're going to have to solve for c. We're going to find particular functions for both of these. The first step is just to recognize that the function y that you're looking for is the integral of the derivative function that you're given. That's fundamental theorem of calculus. Notice that I had to add in the dx. It comes with the integral symbol. Next, you'll solve the integral, and you can do it by any method. I used integration by parts. I also added an absolute value symbol here that's going to be important later on. That should have been in the original problem. Once you've got your solution, which is a general solution because it has a plus c, I'm now going to plug in the point to solve for c. So then you plug in x and y, it looks like this. And once you have your c, your final answer is the function, where you put the c that you solved for into that general solution. I included a second example here just to connect this to something we did much earlier in the year. If we started b the same way, we would say the function y is going to equal the integral of the derivative, dx. But this is actually an integral that we can't take. U substitution, integration by parts, neither would work for this one. And so there's another way to figure out what this function should be. Anybody remember what we can actually do? Right, we can use a definite integral. So instead of just using the indefinite integral, if I were to write y equals the integral from 3 to x e to the sine x dx, this now represents a specific solution to this integral. And this particular solution, if I plug in 3 for x, is going to give me 0 for y. Well, I don't want it to equal 0. I actually want, if I plug in 3, to get 1 as my y value. So I can just tack on a plus 1 at the very back. And this is a function. This is a particular solution to that differential equation. This is actually very similar to what we did a minute ago. The only difference is here we didn't know how to take the particular integral, and in this last example we could find an actual function that didn't have an integral. I've got 2 for you to do. You've already done 1, so check out 2 and 3, and then we'll be done with this video. Great, so we'll talk about definite integrals in class. Don't forget to post a comment to the